So, how many of you guys are familiar with Pascal's triangle? Okay. You've probably seen it in terms of the pattern whereby you start with like a 1, where you start with 3 1s in the form of a triangle. And then you don't have to write it, just watch. Write later. Absorb first, then write. You add these two together, you get that. You continue to always write 1s on the outside. Everything is staggered. Add these two, you get 3s. Add 1s on the outside. Add these two together, you get 4s, you get 6. You get 4, and you have this pattern that goes on forever, right? You have this pattern that can go on forever. Okay, but I'm calling it the binomial triangle, okay? Anybody know why I'm calling it the binomial triangle? Yes.
Because usually the last row added together gets the next row's number.
That's not what I'm talking about. If you're talking about, if we talk about computers, let's say, if we talk about the digital world, we talk about, that's not one. We talk about the digital world. The digital world is a binary world, right? What is a binary world? Can you put up your hand? Okay, go ahead. Yeah.
Is it true or false?
True or false, right? Yes or no? Up or down? Night or day? 2 options, right? If you're going to count in base 2, it could be on or off, 1 or 0, right? Well, this triangle is actually a binary world. That is to say, it involves scenarios whereby you choose or you don't choose. I'll show you what I mean in more detail. How many of you guys have actually used this triangle to get the expansion, the coefficients of the expansion of a binomial? So you've seen something like this, okay? And if this was a 5, for example, you would use the coefficients in the 5th row to actually get you the coefficients of the triangle. How many of you guys have done that? How many of you guys know why it works? Okay, why does it work?
It's because every time you add those, it's because it has a combinational solution that you like 1 choose 5 or something like that. I don't remember exactly.
Because there's a repeating pattern. When we did the a plus b to the power 2, I don't know what grade we did it in. We saw that it was a plus 2ab plus b squared. And then here it's the same thing because it becomes, it's like a repeating, it's like a combination. Like, I don't know how to express it.
Because in the combinations formed by actual multiplication, you have alike terms, and what you have to add those alike terms, and it's sort of mirrored by adding those to the rows above.
Okay.
Is this fixed?
I'm going to.
There's a question.
I'm going to show you things a little bit differently. I think you're going to have kind of like an aha. It's going to be like moment. So, how about this? Let's recognize something. If you went later on in the book, I'm not sure what section, but somewhere in chapter 5, you would also see that, oh, this triangle can be built the following way as well, and you get the same values. I think it's going to be 1. That's n equals 1, that's going to be n equals 2, this is going to be 1, choose 1. Or do they start it at 0? I'm not sure. Can't remember. Can I have a book? It started with 0.
Yes, it started 0.
Yeah, I saw that. I already got that part. Okay.
This question.
Probably should be writing smaller. And I guess there should be a dot, 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 dot. And so on and so forth. I don't know what we want to want. So if you go ahead and you check those numbers, you'll see that those numbers work out to these numbers exactly. Okay? You with me? You'll just trust me on that for now. If you don't, you'll go in your calculator. Obviously, 0 choose 0 is 1, 1 choose 0 is 1, that's 1, that gives you the triple 1. 2 choose 0 is 1, 2 choose 1 is 2, 2 choose 2 is 1, there's your 1, 2, 1, 3 choose 0 is 1, 3 choose 1 is 1, 3 choose 2 is 3, and so on and so forth. Sorry, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1, and you get the pattern. So my question to you is, here's a question. I'm telling you that this is a binomial triangle. So where you have yes or no, up or down, 0 or 1. How is this thing binomial? Because here I see 3s, I see 4s, I see 2s. How is this binomial? What makes this triangle binomial? Yes.
When you, for example, say a plus b to the power of 3, when you go to the row 3, you can get the coefficients from here.
Okay, forget binomial. You know what I mean. You're taking it to mean only, right. What makes it binary, rather? What makes this binary? Why is this the binary triangle? You know what? I don't even say binomial. I could say the binary or binomial. Yes.
Can it be because, like, if you start at 1, for example, 0, 0, you either have a left or right, like a true or a false. And then if you choose 1, like false, then again, you only have true and a false. And you keep, this pattern keeps repeating.
Yes, I think you've got it. You know, but, so how is this binomial?
Because, like,
where's the duality in this 3 choose 1? I don't see a 2 in there.
From the previous one. Because that's 2 choose 1, you have 3 choose 1.
Where's the duality in 4 choose 3? Yes, Michelle.
I feel like for every number, it has its, like for every individual number, it has its yes, it has like its maximum and its minimum. And no, I don't know how to, like it's a yes or no. So for example, like a 3, it has its no, which is 0, and then it's a yes, which is another 3.
For every single one of these numbers, the only option is choosing a value
or not choosing.
Choosing an object, if you will, or not choosing. 3 choose 2 refers to the number of ways you can choose or not choose 2 of 3 objects. In other words, if you think about all of the lead values here, the 3s, here we have 4s, here there are 1s. We're only letting you do 2 things with these things. We're letting you take them or not take them. If I was dealing with a trinomial situation, maybe you could take, not take, or break in half. Right? In a quadrinomial, I don't even know what the word would be, scenario, you could, maybe it could be thinking of painting. You could paint it red, white, blue, green. So then you'd have 4 choices for each. And we could build that formula. There's a general formula. We will build that general formula. But in this case, for every single one of these calculations, even though they don't all have 2's in front of them, it's still a binomial situation because you are limited in terms of what you can do with an object. You can either take it or not take it. So this is a binary triangle because for each n choose r scenario, you can only choose or not choose an object. Can't do anything else with it. When it comes to the binomial expansion, which we'll discuss again later, when you expand binomially, what happens? You basically have, let's say, a plus b to the n. So let's say you have a bunch of a plus b's in brackets. If you have a plus b squared, you have 2 in the sequence. 2 factors of a plus b. If you have a plus b cubed, you have 3, you have 4. But when you expand, what happens? You have a's and b's either being included or touched or not being touched. Okay? You can't take them and like cut them in half or do anything else with them. When you expand, this thing, you're going to have terms with different quantities of A's and B's in them. So either they're in or they're out. There are different quantities of them, but they are in or they are out. So for example, if you use this one, this would correspond to that scenario, 1, 2, 1, which would correspond to A plus B squared, right? If you take a look at something like A plus B squared, what you have is A squared plus 2AB plus B squared, right? Now that's really a 1, and that's a 1. And you can see that that lines up. That lines up nicely with this. Right? And that lines up nicely with this. But notice, this is critical. This says 2 choose 0. This says 2 choose 1. This says 2 choose 2. How can you reconcile this line of thinking with on or off, choose or not choose, with the logic of what takes place when you expand this? Yes?
Is it that, for example, A, it's going to be A multiplied with A or A multiplied with B? So A, like an object A could choose only another object A, or could choose option B.
More specifically, what I would say would be, there are different ways you can rationalize the system for yourself. You guys are doing this? What is this?
It's just
More data questions? Okay, I'm fine with that. Do you guys want to work outside maybe?
well.
What do you prefer?
Are we making? Like, are we disturbing?
Yeah, it's a little annoying, right? So if you guys want to work outside. So you see the first one says 2 choose 0? And you see this one says 2 choose 1? And this says 2 choose 2? You guys see that, right? This is the same thing as A. This is the same thing as, if you will, I guess, AB plus AB. This is the same thing as B. Not to be confused with dot product, but most of you guys know what dot product is anyway. So, if you know what dot product is, no, I do not mean dot product. It doesn't matter because these are not vectors anyhow. So, there's a 2 across. What are you going to associate the 2, the upper 2 with in terms of this? What could it mean?
A and B.
A and B? I say no. I like that. I like that. That to me makes sense. He says only B. Why does it make sense that these 2's refer to only B's? Somebody else. Obviously you know why. You just answered that question. How many B's do you see here?
Oh, because for each B they have
How many B's do you see here?
0.
Okay? And I shouldn't have even written this one like this. How many B's do you see here?
1.
And how many B's do you see there?
Oh.
What is the maximum number of B's any of the simplified terms can have? You see, will there be 3 B's anywhere?
No.
How many B's do you have here? 0. B to the 0. This is B to the 1. This is A to the 1, B to the 1, right? So you go from 0 B's, see, 0 B's, 1 B, 2 B's. 0 B's, 1 B, 2 B's. So the way I like to think about it is 2 choose 0 corresponds to the, now here's the kicker. It corresponds to the number of ways you can choose 0 B's. I'm going to repeat. The number of ways you can choose no B's from a maximum of how many?
2.
So if you follow the pathway, how many ways can you choose no B's? You know this from anything. How many ways can you choose nothing?
One.
One way. You get a 1 then. Okay? Now here's the thing. If we were to write this down here in a general sense, we can think about this as one. Well, I guess if we take a look at this, rather, we take a look at this. We have a to the 2, b to the 0, which can be thought of. This is a to the n minus r, b to the r. Does that make sense? In other words, r is the number of b's that you take from the n available. So, in other words, when you take 0 b's, how many a's do you have? You have n minus 0, which is n, in this case, 2. So, I had a point here, and I don't even remember what it was. Yes, I do. I think. So, if you notice here, when you take n minus r and add it to r, n minus r plus r gives you what?
N.
So you'll notice that the sum of the exponents of the variables, forget the coefficients, the sum of the exponents of the variables is always n. 2 plus 0 is 2, 1 plus 1 is 2, 2 and 0. This is actually, you can think of this as plus a to the 0, b to the 2, right? So the sum is always 2. In other words, one way or the other, you're going to always have n things hit. You may have no b's hit, but if you hit no b's, you're going to hit 2 a's. If you hit an a, how many b's are you going to hit? 1. If you hit no a's, you're going to hit 2 b's. Well, why does that happen? It's because of the nature of the expansion, right? If you start here, okay, you're multiplying. Multiplying is hitting or touching if you think about it, right? You have a number or a variable next to a variable. If you start here, you can say, oh, I can create a term by going this by this. That first move gives you that first term, which is a squared. That involves choosing 2 a's, but we're defining things in terms of number of b's that we choose. Let's go on. Let's talk about, so if we talk about that first step, that involves choosing how many b's?
0.
And how many pathways generated that? 1 pathway. Now let's talk about choosing 1b. There are 2 pathways. Because watch, if you continue with the expansion, that pathway generates an AB term, right? This isn't nice. I gotta go this way. But that pathway, so that pathway involves getting an AB term, which is 2. How many B's do you get? 1. You touch 1 B. And when you follow this pathway, how many B's do you touch? 1. 2 different pathways for touching 1 B. As a result, you get the 2. 2 different ways of touching or choosing 1B. Last pathway,
BB.
is the pathway for choosing 2 out of the 2 possible B's that you can choose. How many pathways generate that? 1 pathway. 2 choose 0, 2 choose 1, 2 choose 2. Right? If we were to do this for a bigger expansion, like a trinomial, right, and so on and so forth, you find the same pattern. It gives you the total number of pathways you can choose. No B's, 1B, 2B, or a maximum of 3 B's. Got it? That's the way I like to think about it. The book doesn't talk about that, but I think it should. I think it's important. So a more general formula for this expansion could then be written as follows. A plus b to the n can be thought of as, well, you notice that for each of these scenarios, the top is fixed. And the top corresponds to this variable n, which is the exponent of the expansion, right? And so whether or not you're choosing 0, 1, 2, you're always choosing from the maximum number of b's that there could be, and the maximum number of b's that there can be are always n. So the coefficient associated in a general sense with any term always starts with a combination n at the top, right? Now it's going to start, if we define things as the total number of ways you can choose no b's from a maximum of 2 or a maximum of n, then it's always going to start with choosing none. And that's because b is typically written as the second thing here, right? It's not written as b plus a, it's written as a plus b. Now, of course, I've already told you that the sum of the exponents of a and b always add up to n. And since the first coefficient, which represents the number of ways you choose no b's, is always going to be 1, and rather, since the first coefficient corresponds to choosing no b's, if the sum of n and r always add up to n, if you chose the no b's, then you got all a's to start with. And so that means this coefficient always has to be n. Because if your first term involves no b's, then to sum the exponents to n, that's all n. Because guess what this exponent is? 0. Right? Your next term is going to involve choosing the number of ways you can choose 1b. Now, of course, that's going to drop down by 1. That's going to go up by 1. Then a couple of b's. Okay, you want to let them in?
No, they're not.
Dot.
Wait a second.
You guys can let them in.
That's the.
And then ultimately you're going to come to a scenario where you're going to have n choose
R.
And
Or,
n minus 1, right?
Wait,
Because you're going to be 1 below.
oh yeah, so n minus 1.
Why is it 1 minus? Why is it minus?
Well, because, take a look here. This is the second last one for this one. You're choosing 1 less than the maximum,
Oh.
right? You guys can come in now.
N minus R.
Now, that, notice, this always goes with this goes with this goes with this. So this is n minus 1, right? If the two have to add up to n, then that's got to be a 1, right? Because 1 plus n minus 1 gives you n. And then lastly, you'll have n choose n, a to the 0, b to the n. So here's your general expansion, right?
Okay.
No good?
That's.
Was there a mistake up there? Oh, there's one thing missing here.
Okay. Well, that's not.
Okay, Ronald, what's up?
Okay, then I get it.
As you do specific
awesome.
examples, I think those will reinforce your understanding of the general formula. Now, what we have to do, we have to establish n and r visually in the context of this binary triangle that we know as Pascal's triangle. And as you can see here is that the n's clearly correspond to the number in the top of each combination, right? So what they do is they create rows to start with. So the top of the thing is going to be called n equals 0, then this thing is going to be n equals 1, and this guy is going to be n equals 2. Makes sense, right? Because your n's are the top values, right? N equals 3. Are you guys following this? And so on and so forth. You'll notice something though. For each of these, regardless how long the expansion is, and by the way, does this only apply to expansion of binomials? No, this is a particular application of this line of thinking. This does not exist for this. This is a shortcut or a
Detour?
not a detour. This is an expansion formula generated by the logic of this, right? This is an application of this, or this is a subset of this, not vice versa. This doesn't exist because of that. It's the other way around. We're not just going to use this for that. We're going to use it for many other things. You'll notice that regardless of whether you're, I'm talking about expansion, so I'll keep it in that context for now. Whether you're talking about an expansion of an exponent of 1 or an exponent of 2 or 3 or 4 or 5 or 6, since everything starts off with a number of ways you can take b's, i.e. 0 b's, you'll notice, and because of the way the triangle is drawn, if you follow along this diagonal here, the r's, which are the bottom of each of these, right? And choose r, are all the same along this diagonal, which goes from upper right to bottom left. 0, 0 at the bottom, right? Because each one starts with choosing no b's, or zeros. And then you notice that this diagonal, what does it have in common for each one at the bottom? All ones, right? And then all twos, and then all threes. So what we say is that is n equals 0, right? But this diagonal, which if you want to think about goes from the middle or from upper right to bottom left, just visualize that position. This diagonal is called r equals 1, or position 1. Guess what this one is going to be called? Position 2, or R2. This one will be called R3. Or actually, you have to be careful. I'm not sure if they, maybe not. Maybe they start with R0. No, this is R0.
Yeah.
This is an R1, right? Because take a look at those numbers at the bottom. Those are 0. So this is R0. This is going to be R1. This is going to be R2, and so on and so forth. So, for the sake of being able to identify terms and have a conversation, whether it be on paper or audibly, we could look at a term like this, and you could say, well, this is the same thing as term 3, 2, meaning that is in the 1, 2, 3rd row, right? And it is in the 1, 2, sorry, 0, I apologize. 0, 1, 2, 3rd row. So it's actually the 4th physical row, isn't it? Because physically the first row is called 0, 0. So when you talk about T3, 2, if the 3 is the N and the 2 is the R, then 3 doesn't correspond to the 3rd physical row. It corresponds to the 4th physical row. You see that? Technically. So you have to be careful. You can't be like, oh, well, this is in the 1, 2, 3, 4th row. No, it is in the 4th physical row, but it's in the 3rd N position, N row, if you will. And when it comes to the R, again, you might say, oh, this is 0, 3. So you might say this is 1, 2, 3. Why is that a 2? Because this starts as position 0, position 1, position 2. Okay? So you have to remember that. Do you understand? Now, it is true that when you go ahead and you crunch these numbers, you get for this binary triangle these numbers, and it is true that you have this pattern of addition whereby any two numbers above a number on either side of it add to give you that number. So more generally, you could then say, oh, well, T, there are different ways you can say it. You can say anything in the triangle, TNR, is going to equal to the sum of two numbers above it on either side. Right? So you got to think along these diagonals now. So let's take this number 6. Well, if you're going to call 6 row n, then anything above it is in n minus 1, right? So both of these are living in n minus 1, comma something, plus n minus 1, comma something. If you're going to call this position R, this one is in a position 1 before it. So this will be R minus 1. And then this plus this gives you that. Well, if this is in position R, guess what? This one is in the same position. So is this a true statement? This is one way of saying it.
So sorry, how was it again? R instead of R minus 1?
TNR, one sec, TNR, any value, is equal to the sum of the two above it on either side. So if you go above here, this is n, this is in position n minus 1, but, sorry, in row n minus 1. But in terms of diagonal, it's one diagonal before. So it's going to be one diagonal. R refers to the diagonal, R minus 1. This is going to be, again, up one row, which is n minus 1, but it's on the same diagonal. So that R doesn't change.
Okay, got it.
You guys see that? Some people write it differently. Some write it as Tn plus 1 R. Like, there are different ways you can do it, as long as relative to each other, everything works. That's one way you can write it. Do you guys see that? One of the things they're going to make you do is they're going to make you take advantage of things like pattern recognition in this triangle, because there are other patterns that exist in the triangle as well. Okay, and we'll see a lot of those. Okay, as we call them, not just the summation of the terms to give a term below. You'll see other patterns. And I think one of the reasons why they want you to do that is to get you used to building recursive and non-recursive formulas or patterns. And that actually comes back again in the beginning of the book as well. But that is minimal from my perspective, because we're in combinatorics and we want to know about counting. So you guys get that even though, I don't know, this thing says 4, choose 1, the nature of this question is still binary. Again, why is this binary? Because you get Jamie, why is this binary? Even though there's a 4 and a 1, how does 2 come out of this? Where does the notion of 2?
Because you choose like the A's and B's, right? It's like
4 represents number of objects.
and
Let's say 1 is a shoe, 1 is a tomato, 1 is a record, and 1 is a table.
okay.
And there's 1. How does he get 2 from 4? I don't get it.
Like it's because you only choose one. Like you choose or you not choose.
There it is.
Yeah.
You're either taking the tomato or not taking the tomato. You are either taking the table or not taking the table. You are taking the sandwich or not taking the sandwich. You are taking the garbage bag or not taking the garbage bag. But there might be scenarios or applications whereby you want more than just yes or no. Like I said, let's say it talks about painting. Let's say you have 4 objects, right? Let's say you had 4 objects. And for each object, there were 3 colors that you could paint. You could paint it red, white, or blue. Take the American flag, right? That is not a binary situation, right? That's a trinomial situation. For each object, you would now have 3 choices. Here, for each object, you have 2 choices, right? So be curious for you guys to see. This will be a homework assignment. Create. See, notice, each of these generally follows an N choose R pattern, right? That's general. But could you create a general formula for an N or any multinomial scenario involving n objects? In other words, this never stops. Does the number of objects in this triangle stop? No. You could have 10,392 objects. But for each object, you can only paint it white or black. Or you can take it or not take it. But in a, I don't know what to say, heptanomial situation, that's 7, yeah. Or hexanomial, let's say 6. In a hexanomial situation, you could still have the 3,992 objects or whatever, but now there are 6 different things you can do with each of those objects. Right? Physically choosing or not choosing goes well with binary, right? But it doesn't necessarily have to be choosing or not choosing. Like I said, it could be painting or doing some operation to something. Right? Let's say it's a physical operation on a body. Let's say there's a crude operation whereby your options are remove the organ or not remove the organ. That works great for this. Let's say there's a particular operation which is more sophisticated, which involves procedure A, procedure B, procedure D, procedure E. And let's say A, B, C, D, E, 4 different procedures. And let's say those 4 different procedures are standard procedures that can apply to any one of 10 particular organs. Right? That is now a, I guess you'd say quadnomial or quadrinomial scenario. There are 4 different procedures that you can apply to any one of those 10 objects. Object 1 can have 4 different things done to it. Object 2 can have 4 different things done to it. Object 3, 4 different things done to it. ... 9, object 9, object 10, 4 different things done to it, right? The only thing that is common is that for each of the objects, you still have the 4 choices. When you get to a scenario whereby you have a different number of choices for different objects, it starts to fall apart. Right? So there's a homework assignment. See what you can come up with in terms of generating a formula. You can go online, you'll find it, I'm sure. If you go to Wikipedia or whatever, I'm sure they've got a general formula there. Let's see if you can try and figure it out yourself. And let's see if you can make sense of it. That's a powerful thing. That's a very, very powerful formula to know because it has a lot of application and a lot of things. One that comes to mind for me is the theory of thermal fluctuations. The idea of why, how many of you guys take chemistry?
11 or 12.
This would be past 12, but it's related to 12, 11. How many of you guys have heard the idea of dynamic equilibrium or chemical equilibrium? Right? Or thermal equilibrium. So equilibrium is a concept. So why systems settle the way they settle? Why does the system settle this way as opposed to that way? That's the answer right there. If you subscribe to that theory. Okay, so there's application to this stuff. Okay, that's physics, that's chemistry, that's a lot of stuff. And the reason why is because modern mechanics is probabilistic. Right? It's all about likelihood and equally likely physically possible outcomes. But whatever, we can talk more about that once we see possibility. You guys still out here? Do you like it? Okay, that's cool.
Sir, can we give an example or something?
Yeah, but I'm still going to teach you a little bit more theory. I still want to teach you more theory. If you could do the attendance, mark all those folks' names.
No.
Everyone.
No, that's the other one.
If you don't hear a name, just mark them.
So should I just call up the name?
Yeah, that's cool.
Or after?
Now, whatever you want.
Yeah, afterwards.
Now, you will see a formula in the book. You will see a formula in the book that says that the sum of the numbers in any row of the triangle, the sum of numbers of any row in the, what I'm going to call the binary triangle. I'm not going to call it Pascal too much. I'd like to call it binary to hit this home. Equals
2 to the power of n.
Nice. 2 to the power of n. Does that make sense?
Yeah.
I think so too. Somebody want to tell me why?
Because let's look at the second row, and it says 1, 2, 1. If you add up all of them, it would be 4, right? So then it would be n, which is equal to 2. No. So then if you put 2 to the power 2, you would get 4.
Or why?
Logic. I don't know.
Let's say, but I didn't follow.
Because that's the row, that's n.
Let n
number 2.
equal 4. When n equals 4, you get 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. 4 choose 0 corresponds to the number of ways you can not choose any of the 4 objects. 1 is choosing 1 of the 4 objects. 2 is choosing 2 of the 4. 3 is choosing 3 of the 4. 4 is choosing 4 of the 4. And when you add all that up, apparently you get 2 to the n. Well, if you were to write down 2 by 2 by 2 by 2, that's a string of 4 2s. You could think of this as object 1. This is object 2, object 3, object 4. And the binary of triangle, or the binary nature of the triangle, only allows for how many possibilities with each object? 2. Take or not take, take or not take, take or not take, take or not take. Right? So if you were to branch it, take or not take object 1. This is an X, this is a Y, this is a Z, this is an A. Is order being injected here? Yes, no, why?
Yes.
No. Why is it not being injected? Because these are all different variables. They involve the choice of different objects. You will never see reproduction of the same elements across that tree in different orders because they are different objects. It's an X by Y, a Z and A. So this is the object 1. Yes or no? This is the object 2. Yes or no? Yes or no? So when you follow all of the different possible patterns, they're all in there. They're 2 to the 4, which is
32.
In other words, you could take object 1, for example, and then, yeah, you can check. 4, 8, isn't it 32? Yeah, 16. 4, 8, 16. Now, you could take or not take the first, you could not take the first object and then take all of these. Or maybe you take the first object and then not take all of those. Or maybe take the first 3 and not take the fourth. There are a whole number of combinations, or possibilities rather. And those would be physically represented by a tree, right? First pathway, or your first branch, take or not take object 1. Does anybody want me to draw that tree?
No.
Okay, second, growth on the branch, take or not take object 2. Of course, it's got 2 possibilities because those 2 possibilities can branch off not taking object 1 or taking object 1. And it grows and it grows. So it makes sense that 2 to the 4 is the same thing as 4 to the 0 plus 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4. There's a total number of ways you can take none of the objects. Does it make sense that 4 choose 1 is 4 in this case? Yeah, because you have 4 objects and it's the total number of ways you can only take one of them. So either you take the shirt, or you take the shoe, or you take the camera, or you take the lobster.
Okay.
There are only 4 ways you can only take one. 4 choose 2 is a bigger number. Right? 4 choose 2 is 6. Does it make sense that 4 choose 2 would be bigger than 4 choose 1?
Yeah.
Because there are more than just 4 ways of taking a pair. You could take the lobster with the shoe, but you could also take the lobster, again, but take it with the hat. Okay, so you see things get bigger, right? This might also help you with the line of thinking you need for something like this, right? So if you had 3 options per object, what would the 2's become? 3's. And that's all I'm saying. Okay, so I think that's a lot of theory for today, right? That's a lot of theory for today. Did you guys follow the theory? This is why you have to pay attention to my class, because if you just look up at the end, you get garbage. You get garbage. So you have to pay attention, right? You have to take notes, you have to ask questions, you have to be involved. Yes.
For the T and comma R, I didn't really understand that part.
Okay, so you see the whole notion or the pattern here when you see the numbers actually crunched from there, that any number you choose can be written as the sum of 2 numbers above it to the left and to the right, with the exception of ones at the end or that one up there, right?
Okay.
Because there's no number above this on the right. So if you take the number 4, oh, it's the sum of 3 and 1. So since we've defined rows as n, and we've defined these diagonals as positions r, is there a way we can notate or create an equation for that idea in a general way? So visualize, take any value, take this thing. This is going to be the sum of upper left and upper right.
Okay.
When I talk about up and down, I'm talking about n.
Yeah.
When I'm talking about left and right, in the end, I'm going to have to talk about diagonals. Because we define things on a vertical axis, on a vertical dimension, and on this kind of diagonal dimension. So if you take 10, if you label this, let's say you label that number T, you give it a general name, T, N, R, that it's in row N, and it's in position R, whatever that is. Okay. You want to apply it generally. Do you agree that it's going to be equal to the sum of the 2 numbers above it?
Yeah.
Well, if this is in row n, then each of these is in row n minus 1.
Yeah.
So notice, nr is the sum of these 2, which are n minus 1s and n minus 1s. However, notice the position of the 2 numbers above are different. The position of one of the numbers above is listed as r minus 1, whereas the position of the other number above is only listed as r.
Okay.
Why? Because position-wise, which is this diagonal, if this guy is living in this general position R, this one that is above it and to the left is, if you follow the diagonal, one R value above it.
Okay.
So it's an R minus 1. This one, however, is along the same diagonal. So its position R doesn't change. So see that R? The R, this corresponds to the 10. The 10 has position R. This corresponds to the 6. The 6 has position R.
Okay.
Now, of course, the 6 has a row that's one less because it's above, right? And so on and so forth.
All right.
Is that a little bit clear?
Yeah.
So,
Can we do questions?
we don't have much time. You want me to pick a question for you?
I just don't know, for example, what question this would apply.
Oh, there's so many things. But,
4.4.
there's so many things, but
Well,
let's,
I'm on for
I mean, I can just make stuff up,
These are all
obviously,
examples.
but I feel like going towards,
example. This is only my friend.
I'll give you a couple questions.
There you go.
I'll give you a couple questions.
So today we only did everything basically?
No, we still have a little bit more, but it's along this line. Okay, here's some page 287, number 12. I don't know. Page 287, let's do 8, 9, 10, 11, 12. For example. Let's do 8 to 12. And then also, have a question. Write the general, write the unsimplified expansion of minus 2x plus y to the 4. So those are two questions. So why don't we do the most, pick one of the ones from 8 to 12, pick one that you want to do, let's do that together, then let's do the one underneath, and then you guys will do all kinds of questions on your own tonight, and then we will pick up whatever you want.
Ron, who isn't here today?
Who isn't here?
Yeah, because you know the name.
Okay, what's question number 8?
Is Nikita here?
What's question number 8?
Question number 8.
A project of 6 students. Sorry, a project team of 6 students.
Oh, what?
A project team of 6
Give me the-
students is to be selected from a class of 30. So part A.
Wait, select from 30.
Part A. How many different teams can be selected?
Other people outside?
So we have 30 students, right? And we're taking 6 to make a team. Agreed?
Yeah.
So what would the answer to be?
36.
30C6.
Yes. 5, 9, 3, 7, 7, 5.
I'm just going to leave it as 30C6. Number of ways you can take 6 of the 30 objects. The objects are different. Do you care about the order in which you take the objects? No. Okay, B. What's B?
We did something.
Pierre, Gregory, and Miguel
What are the letters P, G, and M?
and M are students in this class. How many of the teams would include these 3 students?
Okay, so how many of the teams have to have P, G, and M? This is easy, this is 2. Of the 30, these 3 are in, you have 27 left, you need to take 3 more, right? Does that make sense? Because there's no variation with P, G, and M anymore, right? What's C?
How many teams would not include P, G, and M?
30 choose 6 minus 27 3. Indirect. Right? What's next? D.
That's it. 9.
Let me see what else I've assigned. Let's do 12. What's 12? What's 12?
The theme park has a variety of rides. There are 7 roller coasters, 4 water rides, and 9 story rides. If if Stephanie wants to try one of each type of ride, how many different combinations of ride could she choose?
What if, this is a question. So the answer is going to be 7 choose,
One
times,
times, yeah.
4 choose,
Four.
9 choose 1. But, and this is X, Y, Z, right? These are different rides. Is there order there? No. If you wanted to include order, you multiply it by 3 factorial, right? Okay, let me ask you a question. I'll make up a question.
Wait, why do you multiply by 3 factorial?
You don't, but
If you want order.
if you want order, you do. But the point is you need to recognize that there is no order here. You understand why there's no order? Because there are different rides. Right? So if you draw the tree, you won't see. Okay, question. How many ways, class is over, right?
No, I have 5 minutes.
5 minutes? Let me see. How many ways?
Wait, is he making another question?
Yeah, I'm just gonna make some. You guys can try some other ones while I think of something that I want to make up.
Don't want him to.
Yeah. I'm not sure if it's going to be times 3. They're all times 8.
And Friday.
No. Fridays are Thursdays. Yeah? Oh, yeah, Friday. Thursdays, Wednesdays, always
Shut up.
Yeah.
Thank you.
Let's do it.
It's one. It's girls team, juniors team, and teams.
So how many ways can an overall choice be made from 5 cans of Coke, 3 hot dogs, 5 hamburgers? Meaning that you can take or not take any one of the objects.
Do this with
So it'd be
Pascal.
5 times 5, no. 5 times 5? No, 8. So you have 5 cans, and each of them has yes or no, right? So 5 times. So for each 5, there are yes and no, so it will be 10 for the first one, right?
So let's see.
Wait, why is it 10?
And
For the
then,
can, in this case, you can, for the cans of Coke,
so
you
one-
can take none of them.
Yeah,
You could take one of them. You could
so
take.
5.
So how many options is that for the cans of Coke?
5 times 2.
5 times 2,
Is that 6 options?
Why is that 6?
Because you
I always forget
The
those
power of
stupid.
6.
Okay.
That 5 cans of Coke is not a binomial scenario in this sense. I mean, it is, well,
You can or cannot.
you can take, here's the problem. Here's where this breaks with this sort of. These objects, you see the 3, those are 3 different objects, right? These are 4 different objects. But in this particular question, I'm basically saying that if you take the first can of Coke or the second can of Coke or the 4th can of Coke, you only take one of them, you get the same result.
Wait, no. Why can't we just say they're different brands?
So you could, but then each of these would be split up into a double option.
Yeah,
That's what I meant.
Number
That's
two.
what, that's what
you
she
were
said
saying,
10
yeah.
before.
Okay,
So it'd be
Because
12
those
this
were
time if we
different,
did
yeah.
that. Yeah.
okay, that's clever. So in that case, if you want to do it that way, that'd be 5 and 5, which is 10, which is 13,
Wait.
and you'd have 13 twos. You'd have 2 to the 13.
Yeah.
Yeah,
You just have 2 to the 13.
13.
But I mean these are identical objects, so the result of choosing one can of Coke, doesn't matter which can you choose. So in this case, you have 6. So this is really an identical object question, right? So you'd have 6 by 4 by 6. Agreed? And that, the only thing is you might have to subtract 1. Why might you subtract 1? Because one of the options in here involves not taking any of them.
Oh, true.
So technically, if you call choosing taking something, maybe you subtract the one case which
Which is where you
corresponds
take
to
the-
leaving them all out.
Yeah.
Oh, but why can't we say 3 cases though? Because each of them has one that you cannot choose as part.
Wait, you mean +1, not -1, right?
Minus
That's an option?
But why one though? Why
You can
not
take,
work?
you can take nothing, so I
Because
cancel.
how many pathways along this tree are going to involve you not taking
Oh,
a
because that's
a can of Coke, not taking a hot dog, and not taking a hamburger?
That's what it's.
You follow the tree, how many pathways will have
Oh, right,
nothing
right.
chosen? One pathway. So you take away the one pathway. Before we wrap up here, can you guys do that on both sides of the flyer picture she had? You know,